Hello guys, I'm a member from Group 2 and this is our group slide. Let me introduce to you. I will introduce to you about the following items: binary search tree, AVL tree, 2-3 tree, red-black tree, comparison, and references. Binary tree has the following properties. Firstly, all nodes of the left subtree are less than the root node. Secondly, all nodes of the right subtree are more than the root node. Thirdly, both subtrees of each code are also the binary search tree. As you see, the right tree is not the binary search tree because 2 is smaller than 3. It means 3 contains a value smaller than it. Sorting operation. Assuming that we have six elements and we sort them in the increasing order because sorting needs to visit all elements. So its complexity in sorting the binary search is the big O(n), and this is pseudocode. If the value is below the root, we can say for sure that the value is not in the right subtree. We need to only search in the left subtree. If the value is above the root, we can say for sure that the value is not in the left subtree. We need to only search in the right subtree. If we want to find the node 4, because 4 is smaller than 8, so 4 should appear in the left subtree, and 4 is bigger than 3, so it will appear in the right subtree, and 4 is smaller than the 6, so it will appear in the left subtree. Then we found it. But if the binary search tree didn't have the element 4, it will return the null. This is a table of the time complexity of searching operation. You can see the best and the average time complexity is a big O log n, and the lowest is a big O n. This is pseudocode. Insertion operation. Insertion operation in binary search tree is similar to the searching operation. We keep going to either right subtree or left subtree depending on the value, and when we reach the point left or right subtree is null, we put the new code there. For example, if we need to insert 4 node, 4 is smaller than the 8, so it should be inserted to the left part. And 4 is bigger than the 3, so 4 should appear in the right subtree. And 4 is smaller than 6, so we insert it to the left subtree, and 4 is the left child of 6. This is a process image. Time complexity and pursuit code. We can find the best and the average time complexity is a big O log n because the length of the tree is log n, and the roster situation is comparing all nodes, so the time complexity is big O of n, and this is pseudocode. Then we see the deletion operation. There are 3 cases for deleting a node in the binary search tree. The node to be deleted is the leaf node. Secondly, the node to be deleted has a single child node. Thirdly, the node to be deleted has 2 children. If we want to delete 4 nodes, and 4 node is a leaf node, so just delete it. If we want to delete the 6th node, and it will copy the value of its child to the node and delete the child. So this is the final tree. If we want to delete the 3 nodes, node 3 will copy the value of the in order successor 4 to the node. Delete it in the order successor. This is the deletion time complexity. Best and average time complexity is big O log n, and the lowest time complexity is a big O n. This is pseudocode. Now we see the AVL tree structure. AVL tree got its name after his inventor George Anderson Wellsky and Landis. AVL tree is a self-balancing binary search tree. Each node maintains extra information called the balance factor, whose value is either -1, 0, or +1. AVL tree is maintained by a balance factor. The value of balance factor should always be -1, 0, or +1. Now we see the sorting and searching operation. Since the AVL tree is also the binary search tree, so its sorting and searching properties are the same as the binary search tree. This is the table of time complexity is the same as the binary search tree. The insertion operation of the AVL tree. This is the AVL tree, and if we want to insert a line into this AVL tree, firstly, we should find the location to insert a new node. We found that 9 is smaller than 33 and smaller than 13, also smaller than 11, but we found 9 is bigger than 8, so we inserted the new node. After insertion, we need to update the balance factor. Firstly, we do the left rotate and then do the right rotate as picked. Finally, we got the balanced tree. Now we're talking about the deletion operation of the AVL tree. This is the AVL tree if we wanted to delete the node 13. Firstly, we need to find the successor 21 and give a notation W. Then substitute the node to be deleted. Remove W. And then we update the balance factor to the right rotate. And finally, we got the AVL tree. The time complexity of the AVL tree. The insertion and the deletion of the AVL tree also have the same time complexity as the binary search tree. We can see the best and the average of time complexity are the same, and it's a big O log n. The lowest time complexity is a big O n. Okay, now we're talking about 2-3 tree structure. 2-3 tree have the following properties. Firstly, all nodes have 2 or 3 child and 1 or 2 data. Secondly, if a node have 2 child, it will have 1 data, and its own data greater than its left child's data, but smaller than its right child's data. Thirdly, if a node have 3 child, it will have 2 data attributes. Left data greater than the left child's data, but smaller than middle child's data. Right data greater than the middle child's data, but smaller than right child's data. This picture is a 2 or 3 tree with correct value sorted. We can see each node of 2 or 3 tree have 2 or 3 children. Sorting operation of 2 or 3 tree. There are some nodes, and we want to sort them in an increasing order, because sorting needs to visit all nodes, so the time complexity of sorting operation is big O n, and this is a pseudocode. Searching operation. To determine whether an element exists, we first compare the element to be searched with the root node. If it is equal to any one of them, the search hits. Otherwise, the search direction is selected based on the results of the comparison. This is the workflow of the searching operation. If we want to find the 5 nodes, we can see 5 is not found so smaller than root data, so traverse through the left subtree of the 8. 5 is also smaller than the left child of the right data. Turn to his left data. 5 is greater than his left data, and there is no probability in the left subtree, so it must be in the middle subtree. Turn to the middle subtree, and we can find. There is a table of time complexity of the searching operation, and we can find that the best and the average case is the same as the binary search tree is big O log n, and the lowest is big O n. This is the pseudocode.